Let's look a little bit more about how this address translation works in terms of what actually needs to be in memory and what the MMU needs. So if we have a particular virtual address, and again, we encounter these constantly. Every time you execute an instruction, you take the address where the instruction is and look up the instruction. Every time that instruction does a move on a memory address, you need to translate the virtual address to a memory address. So all the time. It's going to send that address to the MMU, which in principle has to go look at the page table that corresponds to the virtual page number in that address. That page table's got to be stored somewhere. It's in memory. This picture of memory, of course, includes all the caches and so on. So we look in the page table, get some data back from that page table, and compute a physical address, assuming that it's in the cache. And then we can actually get the memory out. So that's what the picture would look like when we have a cache hit. On the other hand, if we get information for a page table entry and it comes back and says there is no mapping for that virtual address, then we have a page fault. And at this point, the program will have to stop and let a page fault handler work. The page fault handler probably is going to move some memory out of main memory onto disk, move some data out of main memory onto disk, and move some data back from the disk into the main memory. After it's done that, then it has a location in main memory where that page can be mapped. So it sends out a new address back to the MMU, which can then use it to finally get the data. And if we have a lot more data than fits in main memory, then we may end up moving a lot of data back and forth between the disk, which could be very slow. But it's going to work out okay as long as our program has good locality. As long as it's using addresses that are close together, good for caching in general, it's good for caching at the level of pages. We will use memory that we have moved in from disk frequently enough to make it pay off. And there's a concept called working set. That is the pages that are actively being used by a CPU at a given time. And that concept is useful because if your working set gets much larger than physical memory, or gets close even to physical memory limits, then you're going to have to move data back and forth all the time because it doesn't all fit in main memory, and that's what we call thrashing. Again, this is much less of a problem than it used to be now that computers have large main memories, but if your program is big enough, it can still be a problem. How do you avoid thrashing? By having a smaller working set, which you get by having good locality in your program. There's still a drawback to this process. Even if we're invoking the page handler infrequently, every time we encounter a virtual address, which again is constantly, we're having to go to main memory to get an address that we can use to consult main memory again. So the problem here is that it's 2 lookups for every virtual address, and we know how to solve those kinds of problems. We have yet another layer of caching. The layer of caching for resolving virtual addresses, for doing page table lookups, that's handled by a translation look-aside buffer, or TLB. So in your CPU chip, there's actually a CPU and MMU and this extra buffer that's used by the MMU to resolve many addresses quickly. Again, if you have good locality, you are using addresses that were recently resolved at the virtual page number level. And so the translation look-aside buffer will very often be able to give the MMU the address it needs in the main memory without fetching any sort of information. And then the actual information you are interested in, based on that address, can be fetched.